Good morning Year 10, it's Miss Bailey here. For your starter today, there are 3 questions for you to have a go at answering. So pause the video whilst you have a go at these. Okay, so to go through these answers, the colour of phenolphthalein in alkali is pink, and it would be colourless if it was in neutral or acidic conditions. Whereas the universal indicator, this gives us our rainbow spectrum, with our neutral being green at the pH of 7, and then our pH of acid is anything that is less than 7. So normally we'd say between 1 and 6, but it is strictly less than 7. So we looked last lesson about pH, and we said how pH measures the acidity or how alkaline a solution is. But the way in which we work out the pH is actually by using the concentration of those H+ ions that have been dissolved in the solution. So if we have a pH of 1.0, then that means our concentration of H+ ions is 0.1 moles per decimetre cubed. And as the factor of hydrogen ions decreases by a factor of 10, so remember that factor of 10, this is why it's a logarithmic scale, then our pH increases by 1. So the fewer the amount of hydrogen ions, the more the pH increases. So the lower the concentration of H+ ions, the higher the pH becomes. So the key points to note from here is the bits that I've underlined. So pH measures the concentration of H+ ions which have been dissolved in solution. Remember that these get released when acids are dissolved in water. And then also this idea that as the concentration decreases, our pH increases. But the fact that we have a decrease by a factor of 10 leading to an increase by 1, and that's why we have that logarithmic scale. So pause the video whilst you have a go at this. Okay, so with our pH values, we have a table here looking at our H+ ion concentration and the pH value corresponding to it. So I want you to pause the video and have a think about what you notice about the concentration and the pH value. So what you should have seen is that whatever the number the power of 10 is raised to, that is the number of our pH value that corresponds. So when we are doing our standard form, the minus sign tells us we're moving down a place, and 1 we're moving down 1 place, 2 we're moving down 2 places, 3 and so forth. But that also tells us how many places we end up moving along the pH scale. So 1, 2, 3 and 4. So 2 questions for you to have a go at. What will the pH of a 1.0 times 10 to the minus 5 mole per decimetre cubed solution of dilute hydrochloric acid be? And second question, a solution of sodium chloride is neutral. What will the concentration of hydrogen ions be? And give your answer in mole per decimetre cubed as a decimal and in standard form. So pause the video whilst you have a go at those. Okay, so the main part of today's lesson is looking at the difference between strong and weak. So weak acids are acids which are not harmful when dilute or concentrated. So just going to look at some examples of weak acids. So those are ethanoic acid, citric acid and carbonic acid. So these are typically the acids that we would be consuming like our everyday acids, because they are not harmful when dilute or concentrated. So this is an important point to note down about our weak acids. So just pause the video whilst you write that down. So if we have a 0.1 mole solution of hydrochloric acid, so this is a strong acid, we have discussed that that would have a pH of 1. But what do you think the pH of a weak acid of the same concentration would be? So pause the video and have a think. Do you think it will be higher or lower? So if you said it was going to be higher, then you are correct. So 2.9 is the pH of a 0.1 mole per decimeter cube solution of ethanoic acid. So they have the same concentration but a different pH. So I want us to think about why that might be. So pause the video whilst you have a think. I've included a hint there for you as well. Okay, so with our pH we were talking about how it can measure the amount of H+ ions that are in our solution. So if we have a higher pH, like with our weak acid, that tells us there is a lower concentration of H+ ions, whereas a low pH we have a higher concentration. And so the reason for that is because actually some acids don't fully ionize. So when we say that they ionize, we mean about them splitting up into their ions when they get dissolved into water. So you can see in the left picture, the white particles are completely separate from the green particles, so they are fully ionized. Whereas on the right picture, you can see that the majority of those particles are actually staying combined together. So the green combined with the white, there's only one of those molecules which have actually dissociated into green and white separately. And this is how we would show it in an equation. So here our H+ has completely split up into H+ and X-, whereas here we have a reversible change. So it could go forwards, but it could also go backwards. And so what that means is that when some of the H+ ions have formed, they can then reform HX in that reversible change. And so our amount of H+ ions that are in solution is actually lower compared to this example at the top. So this example at the top, we have complete ionization, whereas at the bottom it's incomplete and we can reverse it. So these are the two distinguishments between our strong and our weak acid. So strong acids ionize completely, whereas our weak acids don't completely separate because that reaction is reversible. And this means that we have a lower amount of H+ ions in our solution than more with the original compound that they started with rather than being separate. And this means that it's going to have a higher pH because a low concentration of H+ means a high pH. So pause the video whilst you make some notes on that. In the PowerPoint you'll be able to get the link to this. So there is a video from the start to 2 minutes 28, which reaction was the fastest and how that should say could you tell. And then why did the universal indicator for the final 2 experiments at the end turn purple? So pause the video whilst you go off and have a look at that. So in that reaction what you should have seen was that there was some fizzing which was able to tell us how quickly that reaction was happening. And so if we have equal amounts of sodium carbonate added to beakers containing our weak acid and our strong acid, then we're looking for the difference seen. So with our weak acid, we've got less H+, whereas our nitric acid, we've got more H+. And so thinking about the difference seen, it's all going to be about that availability of those H+ ions to react. Now we haven't looked at how acids and alkalis react, other than that video that you've seen. But in that video, you saw that we were looking at bubbles being produced, so carbon dioxide ends up being produced in this reaction. And so the difference that we should be seeing is the amount of carbon dioxide that we get produced. So where the reaction is happening a lot faster, then we're going to get a lot more bubbles, whereas where the reaction is happening much slower because the reactants are less available, then it happens a lot slower and we have fewer carbon dioxide bubbles. So that's the difference that we would see, because our observations is what we would literally see during that experiment, so looking at those bubbles. So putting this into practice then, so describing a reaction that could be used to show the difference between a weak acid and a strong acid. So this is the experiment that we were just talking about, and we need to be explaining why the weak acid and the strong acid give different results. So that's drawing in the ideas about the complete ionization compared to the reversible ionization. So have a go at those two questions. I will pop an assignment on Teams for you to submit it, and that will conclude your work for today. Thank you all for watching, and see you next time. Bye.